terms of, right? They're telling you the in terms of part here. So a is a constant. It's frozen. Thank you. I'll get that. Thank you. So what does it say to do? Expand the quantity about 0 in terms of the variable given. So you want to turn this into something that is very similar to something you already know the Taylor expansion of, correct? A is a constant. So the first thing you could do is factor out what from the numerator? It's going to be a times this thing, correct? So you have a squared plus x squared to the 1/2. Well, just play around with negative exponents, and what do you end up with? A times what?
A squared plus x squared.
A times a squared plus x squared to the what? Negative 1 instead. If we pull this out, we end up with a times 1 over this to the 1/2. What? And if you take an a out of this, what do you end up on the inside? 1 plus what? X squared over a squared, right?
Yeah, a squared.
Yeah, we factored it, but do you agree that this is, are we okay so far? Is that correct? Yeah, the a's cancel, and you're just left with 1 plus x over a squared to the negative 1/2, correct? And is that a form that you've seen before? Yeah, what is that? Binomial. Binomial. So we could finish this, or do you understand enough to finish this on your own now? So this was all about the manipulation up to the point where you use the binomial expansion. How? Good? Excellent? We good? Okay. Path 1, which is going to be turn this into, or just have a glitch out right there, turn this into 1 over 1 minus x, and let x equal ln of 1 plus t. Is that that's what you wanted to do, correct, right? So you have to write this expansion out. What is that expansion? 1 plus, is it x or 1? What is it?
Yeah, 1
plus, plus x cubed, right? And then if you're plugging in that, so you have to plug into that what? Well, yeah, so you'd have to take this right here and plug that into all of these, right? What's the not so cool thing about that? What's the not so nice thing about this? What is this? Do we know what that is? Is that one of the ones you have to memorize? It is one of the ones you have to memorize. Do you remember what that one is? What does that equal? T minus what?
T minus t squared over 2.
Yep.
Plus t cubed over 3 minus t.
Minus t what?
T to the 4.
It's t to the 4th, right? Over 4, like this?
Yeah.
So the reason that this isn't really what you want to go with is one of the biggest reasons we do Taylor expansions, we turn them into Taylor polynomials, is to translate this function into something that doesn't involve this function. Like when I ask you to define a word, what's the one word you're generally not supposed to use when you're defining a word? The word itself. So by keeping ln in here, what we're doing is we're redefining this, but in terms of itself. Is that a good end goal? Not really. We want to theoretically get rid of, to translate it into a definition that doesn't involve ln. Can we do that here? Absolutely. So this is equal to the blue, correct? So what do we know? If we write this in, we know that this whole thing is equal to 1 over 1 minus what? T minus t squared over 2 plus minus t to the 4th over 4. So technically that is third. So we have this one right here. How many different places can we get the third power out of this? Well, we can get it this times that, correct? What's that going to be? Negative t cubed over 2. Is there another place where we can get a t cubed? Right there, which is what? Over 2. So what's the last term going to be? Plus what? Negative a half. It's going to be just? You add them together. What do you get? Minus what? Minus what? Just t cubed. Yeah, minus t cubed. End up with negative 2t cubed over 3. Is that correct? How do we feel about that? We feel pretty good about it? So on this one, I remember, Sabrina, you were asking me on the... So what do we have here? We have these right here. Are we okay with those? Is there another term? Yeah, look what's over here. Excellent. You have t minus t squared over 2. This one is cubed. What's the only one you're going to have here? the first one, that's going to turn into t cubed. So what do you have here? You add t cubed to this, what do you get? T cubed over 3. And do you sense a pattern going on this, by the way? Yeah, there's a pattern. What is it asking here? It's saying, I think we're supposed to estimate, what is it? Use theorem to find a bound for the error in approximating the quantity with a third degree Taylor polynomial for the given function. Compare the bound with the actual error. We did one just like this. So what's the first thing you need to write down? It's the first thing you need to write down is n equal in this case. So in this case, we're doing 5 here. N is equal to 3. Exactly. So that means if we use the statement that's on the board that needs to be an automatic, our error bound right here, our error bound is of x like that is going to be what? Equal to, and yeah, so it's going to be 1 plus x to the negative 1. So does this actually cascade rather nicely in terms of derivatives? Yes. It does. So the f double prime of this is going to be what?
Negative 1 plus x to the negative 2.
Negative, yeah, 1 plus x to the negative 2. And then triple prime, Lydia, is going to be what?
2 times 1
yeah.
plus x to the negative 3.
Right, so you have 1 plus x to the negative 3. And then the fourth derivative is what?
Negative 2 times negative 1 times negative 3.
Yeah, so I'm, correct. So I'm writing this out just in case we need to actually see a pattern to this. So we have, nice, we have this right here. Okay, so that's F4. So the question now is, so you simplify this, you know that you end up with, what is it, negative 6, I think? Negative 6, 1 plus x to the what? Still negative 4, right?
Yeah.
So we have this as our fourth order. So Sabrina, let's get to your sticking point. This is what you asked about before class, right? So you have this function right here. Negative 6 times 1 plus x to the negative 4th. You have the fourth derivative. Yeah. Do we agree that that's the fourth derivative? Yeah. Right? So what is this telling us? We need to find the max right here. We need to find the max of this function. On what, though? On what? Does it give us an interval? That right there, what is that? That's the actual value, right? What is this? That's our approximation using the third degree Taylor polynomial. So how do you find the actual error? 0.4055 minus 0.4167. And what do you get as our actual error? What's our actual error going to be? 0. What? 112. So this right here is the actual error. What was our maximum projected error? Take a look, everybody. What was n? 3, so it turns into 4, that's fine. And we're maximizing that from 0 to what? 0 to what? Yeah, it's 0 to a half again, right? Why is it 0 to a half? Because the polynomial is centered around 0, Sabrina, and what are we plugging in? We're plugging in 0.5, the a value, like what we're going from and to. Okay, so, because what are we plugging in to get this? What do you plug in to get 0.5? What do you plug into this? You plug in a half, so it's going to be 0 to a half. Because that's what the polynomial is centered around. So we now need to take the derivative. So what's the first derivative? What's the second derivative? What's the third derivative? And what's the fourth derivative? Do that by yourself right now. Please find me the fourth derivative. Find me the...
0 to 1 half.
And are we totally clear on why it's 0 to 1 half? The interval is always the a value to x. A value to x. In this case, what's the a value? 0, because that's what it's centered around, all the way to x. In this case, we're plugging in a half for x. Okay, so we need to maximize this. Now, again, are we back to calculus 1? Yeah, we're back to calculus 1. We need to figure out, is it 0, 1 half, or somewhere in between where it's maximized? I'll let you guys figure that out for yourself. Be careful. X is what? So we've still, what's interesting about this is the examples we've done have all been done by straight logic. Theoretically, this could be a polynomial going like this, and you'd have to take the derivative and then set it equal to 0 and solve it. I've already warned you about that. So it's when x is equal to a half. So what do we plug in? A half. So the max will be, yay, 80 over what? 81. Times 1 over the cube root of 1 half to the 11th power, right? Nice. So in this case, it's equal to, you can just write it as 80 over 81 times 2 to the 11 over 3. It becomes positive because 1/2, 2 to the negative 1, it jumps it up. So this right here could be a great question. As that would be, if you did out the decimal, this is the only thing you need a calculator for, you end up with 0.0 what? 33. So that would be the max error. But what do they ask you to do for the second part of this question? They ask you to do what? Compare it to the actual. So the first thing we do is we say, okay, on our calculator, do this for me. What is 1/2 to the 1/3? Someone tell me what that is. Raise your hand when that is the m value. Absolutely. So let's just finish this first. You're absolutely right. So it's going to be 80 over 81, 2 to the 11 over 3.
Why is it 2 to the 11 over 3?
Because this right here, right there, that is the cube root of 1/2 to the negative 11th power, right? So that is the cube root of 2 to the negative 1 to the negative 11th, which is 2 to the 11/3. The negative kind of trickles up. So if we want the actual max error, thank you for pointing that out, Katie. We just figured out m right there. It's m over what? M over 4 factorial times, in this case, what are we plugging in? 1/2 to the what? To the 4th right there. So this right here turns out to be 0.033, which is the max what? Error. So we want to compare that to the actual error. We go over to, excuse me, I'm bouncing all over the place, I'm very sorry. We need to actually do 1/2 to the 1/3. What is 1/2 to the 1/3? Someone calculated it for me, right?